Okay. Welcome everyone. Thank you for joining my talk, Harnessing Constexpr Path to Safer C++. My name is Mikhail Svetkin. I'm working at Remarkable. We're building such beautiful paper tablets, which we... Yes, Anders has a tablet here, if someone want to try it out. Yeah, we claim that they're better than paper. Mostly I'm working on architecture and internal frameworks and libraries and build systems. And that's enough about me. So, what we have on our agenda today is we will talk about is C++ a safe language. We will look at the common pitfalls in C++. We will look at the traditional solutions, how to cut these common pitfalls in C++. We will talk a lot about Constexpr. Mostly about evolution, how we can use it to address the issues, what's the limitation, how to write the tests, and we will try to summarize it. So, in practice, what you're going to learn today is that it's super easy to do a mistake in C++. We will look at how to protect ourselves from those common pitfalls, and how Constexpr could help you here. Okay, let's start with very cheesy and weird question. Is C++ a safe language? And yeah, here there's someone say no. It's a good answer, but let's look from the news perspective. A couple of years ago, I think it was 2023, in December, I think it's American agency, NSA, who published that article that recommend adoption of memory-safe programming language. And then another one was CISA. I didn't actually know about these agencies before, but apparently they're very important. And after that, for the last 2 years, I think everyone talking about, like, okay, we need to adopt memory-safe languages. Memory safe, memory unsafe. Google published the paper, Security by Design. They were encouraged to use memory-safe languages. Microsoft Azure announced that they not write new code in C++. So there was a lot of news. And I think if you haven't seen that talk, I would really recommend. Helge Penne, last year at NC Tech Town, summarized everything pretty good and basically explained what's the threat for C++. But if I do TLDR basically and summarize it quickly, everyone says do not use memory unsafe languages in your products. Use memory safe languages. And specifically, they say language, I think. And as they say, rewrite in memory-safe language. And I highlighted R. I guess you understood which language they meant, right? And if you skipped all this news, you might have questions like, what is wrong with them, right? Why? We all know that C++ is the best language, right? For the audience, people are laughing. Frontline people here are laughing. But I think it is the best. But yeah, if we just highlight things, they always say memory unsafe language and memory safe languages. And honestly, a couple of years ago, I didn't really knew what these terms mean. And I think they was not that widely used, I would say. And then when I was preparing talk, I decided to go to and Google what is the memory safe language. And I went to there is apparently an article in Wikipedia which says that memory safety is the state of being protected from various software bugs and security vulnerabilities when dealing with memory access, such as buffer overflows and dangling pointers. And it refers this paper, which has some explanation, but when I read it, I kind of not really understood the whole point. And then I Googled it more. And I found that there is Open Source Security Foundation, and they basically, I think they define quite well what is the memory safe by default language. It's basically which prevents following errors, things like access errors, invalid read and write of a pointer, initialized variables, memory leak, race conditions, and undefined behavior. So if we take this kind of definition of memory safe language, I would ask you, rephrase the question and ask, is C++ a memory safe language? What you would say?
I'd say yes if you use it contemporarily.
I would disagree and say no. And I will explain why I disagree. Let's look at the common pitfalls right now in C++. And for that, I actually went to a website which provides top 25 common security errors. And there is this 5, which I highlighted. It's out of bound write, out of bound read, use after free, null pointer dereference, and integer overflow and wraparound. And let's see how easily we can reproduce some of these errors in C++. So I have a function which accepts some span of characters. And basically, we're trying to create an integer, for example, out of the text, basically parsing the string and get the integer. Is that function looks okay? And by the way, this is the moment where I start beginning to talk to you guys, and I need some response. So is that function looks okay? Do you see any bugs in there? You can say yes, no, nod, or I see that people are questioning. They don't know. But I will say this is okay function. There is no errors right now. Just to highlight. There is?
Yeah, the fail to parse is dangling if you create it. Oh, no, it's not.
No, it's not dangling because it's a literal, string literal, so everything fine. But you get to the point where I'm going, yes. So let's say someone later decided to refactor that function because fail to parse is not enough as an error. It decided actually to print what's the error code. And we added std format. Does that look okay? Let's say okay. No one say, so let's, I see the one person is nodding, good. But I will prove that it's okay. I wrote the tests. Look at my tests. So this is a catch-2 framework, by the way. So I'm passing the 10 as my string. I'm saying from blob. I'm checking if there is a value. And I'm saying 10. And then I'm saying string view some invalid input. And it says error 22. I'm just checking that invalid. So basically, I wrote the test, right? And I run them. They pass. They pass. And then production something fails. And if you know that, can you say what's wrong with that function?
Return a string view.
That's okay. We can return string view. What's the problem?
But string view is a reference to a string, not an actual string.
Right. So the function returns a string view, but std format returns std string, which is implicitly converted to a string view. And basically, we got not a classical one, but I would say use after free. So the string has been delocated already, but we're still allowed to use it. And our test didn't help us to cut it, right? So that's one of the common pitfalls. And there is no any help from C++ as a language to prevent it right now. Let's go further. So let's say, okay, we decided to refactor that function, and we decided, okay, we were not going to format, we'll just return the error. That looks okay, right? No mistakes here so far. I'm just saying it's okay. Okay, let's go further. We're running our tests, everything is passing, and production is passing as well. Good. And then we decided to use that function in other code. Some other developer come and decided to use it. And it's basically there is some parse header function. We get some strings, string views, and we want to, at some point, we want to take the second element in the span, and we basically want to parse it. Does that function looks okay for you? Any errors or anything?
Doesn't check.
Right. What I don't check?
That expected actually contains the value.
Yeah, that's good code. But again, I wrote the tests, and I run it. Like I supply first of all like a string with version 1, with the version 2, and the production again failed. And we went there and we see that yes, I don't check, right? That's kind of sad. And particularly, for example, if input is, oh yeah, I forgot to say, it doesn't really fail as you would expect. I actually tried on all the compilers. So it is undefined behavior. Like I'm trying to get the value of something that contains error right now, expected. But since std, that was here. 1 second. std_rc, it's an enum. It's technically integer. And the value is uint 32. So both of them, it's a union. They're in the same union, right? So accessing to it will actually give me a version 22. Even though it's undefined behavior, but mostly compilers will give it because union, it's the same memory, right? So it might lead you to a really, really tricky bugs. So your application will not crash. It will just continue working, but very, very unexpectedly. So yeah, I would say it's a dereference without the check. I think it's quite classical, more with the pointers, but I think when we get these smart classes like expected, optional, and smart pointers, it's kind of the same issue. So yeah, we could work around it. We can do, okay, if the version hasn't value, then return unexpected, and so on. Okay, now I decided to deploy my code again. Okay, my test passing, that's okay. We added the test case for invalid version. Everything is good. But then production fails again. Something went wrong. What happened? If someone see another error here. Yes, please.
How do you know that you have a second element in input?
That's a very correct answer. Yes, I'm not actually checking that input contains any elements at all. Maybe it's somewhere, if the function is too big, maybe someone checked it at the beginning, maybe it wasn't, right? So I think it's like a very classical out-of-bound read. And we always say that we need to write the small functions and there is a good practices, but in reality there is a lot of code. The chance that you did it by mistake is quite simple. And again, it's undefined behavior. It might work, it might doesn't work, wherever it will be, right? So let's go to a completely different example. Probably you've seen such functions where you have something loading, like setting synthetic example, loading from a file and return the Boolean. And it looks okay, no problems here so far. But then you would look at the size, it's 500. Now you're starting to worry, right? It's not a small function anymore. And somewhere 40 lines down to the function you see malloc. Yes, that's my reaction. And then usually I'm going down, like, okay, is there a free? And I was like, yes, there is free in the end. Good. Well, so far, you're right. It's not good. Because somewhere in the middle there is return, right? So what's happening is we're getting a allocation, and then something happened in the middle. We're returning the false, and we forgot to free the memory, right? It's kind of a memory leak, right? Pretty common. Probably have seen this, right? Okay, so this is like a couple of examples of pitfalls. And there are a couple of reports from Microsoft that 70% of common vulnerabilities are tied to the memory safety, like things I showed you. And Google Project Zero Team also said 67%. I think if you attended different talks to similar topic, you will see that everyone reports it's like majority of issues like this. So now let's quickly take a look how to prevent such issues. There are traditional solutions, and if you attended the keynote, it's not something new, you probably already heard. There is static analyzers, which basically detects the issue before executing. They're just basically analyzing your files all the time, right? You don't even need to build your program. There is sanitizers, which detects the issue during the execution, so you have to build your program and then execute and then see results. And let's go step by step. So this is my experience and overview of static analyzers, that they mostly detect only semantics issues of the language, like, oh, you forgot to do that and that. They generate sometimes false positive. They're usually very limited to translation unit. They don't really understand about everything, about your code and how that works together. They're limited to predefined rules. For example, I will show you example with the reference, right? And clang-tidy, one of the static analyzers, has it for optional, but doesn't have it for expected. And it's pretty kind of the same semantic, but you cannot even extend it. You need to wait a new version of clang-tidy if they added the support there. It does not detect any concurrency issues because it doesn't run the code, right? And it's kind of increasing the build time because in parallel, you're building, the static analyzer is always running on your code. So you can say it's increasing the build time in a way. As for the tooling, there are plenty of tools available. I've highlighted the few which very commonly known, I think, CPP Check and Clang Tidy. There is SonarCube, and there is plenty of other free and commercial ones which you can buy. And recently I actually learned that there is built-in analyzers in compiler. You can just pass the flag and that will enable them. So pretty interesting. And then if you use the best build system ever, CMake, it's super easy to integrate. You just need to set a couple of variables, couple of flags, and that's supposed to work out of the box. So let's do some case study here. So let's imagine that I have a project where I enable everything and run on all these examples which I showed you before. You will probably be surprised by the result, but use after free, the example I show you, none of the static analyzers detected which I used. The reference will also was passed because it was not an optional, so no one understood that. Out of bound read was also passed, and the only thing was detected is actually memory leak. Probably it was pretty obvious to look at the function and see there is a return, and yeah. So let's go further. Sanitizers, and this is in my opinion which actually kind of a game changer. They don't give you a false positive generally. They actually provide you with the real understanding what's happening in the code and errors. There is some downsides that you need to compile in special mode and run it. So it's not pretty well working when you do cross compilation, or if you're, it actually also requires to have operating system as far as I know. So you cannot just use it for microcontrollers without OS, for example. I think Windows has not really that much, or MSVC compiler doesn't have anything there almost, except I think only address sanitizer. We'll talk a bit later. Yeah, and you need to have a good test coverage because basically you need to compile your program and then you need to run and you need to go to that path which actually failing. You get a lot of runtime overhead. It depends on what kind of sanitizers you enable. Your performance can go down. Memory usage rise up. So you wouldn't probably use it in production. Ads increase the build time, binary size as well if you're limited on these things. And sometimes reports are really hard to read, but it's possible. As for the tools, there is 5 different sanitizers. Other sanitizers which is available for, it's basically for detecting use after free things. This is available on all major compilers. The other 4, I think, if I'm correct, they're available on Clang, and some of them available on GCC. I don't remember, maybe everything on GCC available as well. But basically, you have a leak sanitizer to detect memory leaks, thread sanitizer to detect race condition and deadlock, memory sanitizer to detect initialize variable access to it, and you have undefined behavior sanitizer to detect undefined behavior, basically. So again, if you're using the best build system ever, it's super easy to enable it. You just need to pass a flag to the compiler, and you need to pass it as a compiler for translation unit and also as a linking thing. And let's look at the case studies. So use after free was immediately caught, so I wasn't able to pass the test. Memory leak was caught. Parse header version 1, we're actually supplying the valid data. It's actually, the sanitizers couldn't say anything because we didn't went through the path which is actually undefined behavior. So you have to actually have a test which covers that thing. So if you don't have a test coverage, sanitizers will not help you here. So again, if I say like a different input but valid one, it will not detect it. And only when you have actually invalid one and you go through it, then the sanitizers can tell you, okay, this is an error. It was easily called the out of bound when I supplied the invalid input as well. So it's pretty good, but it requires you to have a huge test coverage. So just some summary of traditional solutions. So I would say static analyzers are good for checking the semantic. There are some rules which you can detect by looking at the files, which is okay. A lot of false positive, but it's usable. It has its own thing. Sanitizers, in my opinion, actually detects the errors, so really encourage to use them. You have to pay with increased build time. It's sad, but we have all the powerful PCs nowadays, right? There is some runtime overhead, so you cannot use it in production, sadly. They are not enabled by default, and it requires configuration, what you want to actually detect, when you want to detect, so you need someone actually who knows that. So if you don't really know what you're doing, you might well not able to get anything from there. Okay, that was the traditional solutions. What else can we do? Does anyone have any ideas? Constexpr, great! We can Constexpr all the things. For those who doesn't know, this picture at least I saw from the Jason Turner and Ben Dean when they presented how to do parsing the JSON at compile time. It was quite cool talk, so I really recommend you to watch it. So, but now, 8 years later, basically, you cannot say that we can do all the things Constexpr, but we can say most of the things now are Constexpr. By the way, how many of you wrote any Constexpr code? Just raise your hand. Okay, a lot of people. That's good, good. But we will go through the basics for everyone to understand how it works. So, Constexpr was introduced as a language feature and as a specifier in C++11. And you can mark your variable over the function, which says when you mark it, then such functions or variable can appear in constant expression. And if you're wondering what is the constant expression is, you need to go and read the long list of what it is. But it's basically, it says like, it's a core constant expression unless, and there is like a list of exceptions. But one of them is very important because it says an operation that would have undefined behavior. So by design, in Constexpr context, compile time, you cannot have undefined behavior, which is pretty niche, right? So it's like there is 0 UB in Constexpr, unless there is a bug in compiler, which the compilers have without the bugs, right? And in C++11, I think there was no any library features to std. I don't think there was no any Constexpr usages there. But let's write a simple example. So I have a Fibonacci function, which, as you can see, I marked with Constexpr. I mark the function and I mark the variable. You have to do it in pairs to be able to achieve the compile time evaluation. And what's happened when you mark it with Constexpr? The compiler will see, okay, this is a variable, and we're calling the Constexpr function, so it will compute your result of the function and assign it. And basically, if you do assembly, you will basically see that it's putting the 55 the answer. And by the way, if someone curious why I wrote it with the question mark and I forget how to correctly pronounce it, it's ternary operator, I think. Yes. If you're wondering why did I wrote it like that, it's not like I love it, and this is my choice of style, but this is the only condition you can use in C++11 in Constexpr. Nothing else was allowed. You couldn't create a variable, you couldn't use if, else, while loop, and anything. So this is the only way. So, yeah, that's how it works. Does anyone see a mistake in that code? There is an error, it turns out. When I did a dry run at the local Oslo C++ meetup, one of the participants mentioned that I have an error, and I didn't know. Yeah? That's true. That I didn't test as well. What else? Someone said that there is if I pass the negative integer, that would be an error, right? What else can I do to break? Yes, but that's not that important. Okay, I will give you the answer. So what happens if I say count 47? And I try to compile. Compiler will actually help me and say, Well, your constant variable is not anymore not initialized by constant expression. And it will tell you value, big one, outside of range representing value of type int. So we have an integer overflow right now. And the Constexpr actually caught it. Of course, if you have actually a test for that, right? But it's kind of cool. The compiler tells you exactly what went wrong, right? It's super easy and quite easy to understand, read, and yeah. It's a powerful tool. By the way, I have to warn, most of the warnings here is provided by Clang, because GCC and MSVC sometimes give you really like long list of explanation, very hard to read, so Clang is the best. If you have a possibility to use Clang in this case. But MSVC and GCC will give you the answer, just bigger. But we'll get used to it, I think. Okay, going forward, C++ 14. On the language side, we finally can use if, else, for, while, do, while, and we can create variables. And then the library, standard library started to get, for example, Constexpr was, as a keyword, added to many functions in header complex, in chrono, in utility. Some functions of stdarray has been marked Constexpr, not all of them, not sure why. And stdtuple as well was, some of the function was marked Constexpr. So if we go to the code, we can rewrite our Fibonacci differently. And now we have a variables for loop, which is very good. But the same way, it works the same way. So when you start to compile, compiler will look at the, okay, this is Constexpr variable, Constexpr function. I will compute and put the result here. So everything is great. C++ 17. This is where a lot of cool things started to appear. And one of the things you got is Constexpr lambda, which I thought was available all the time, but it turns out they was available only from C++ 17. You got special condition if Constexpr. We will look into that. And more standard library features has been marked with Constexpr keywords. So let's look actually at the lambdas. Who thinks that this code will compile? Or who thinks this code will not compile? Just raise the hands who think that will compile. 2, 3, 4, 5, 6, 7, 8. Okay. Who thinks it will not compile? Couple of people. Okay. You might wonder I think the misconception or thinking here is, okay, we have a Constexpr variable m, but lambda is not marked Constexpr anywhere. And the answer is it will compile because lambdas by default implicitly Constexpr if it's possible, so you don't have to mark anything. That's why I thought this was feature available from C++ 14 or 11. But it turns out no. It's just implicitly Constexpr if it's possible. If it's not possible, then you will get an error. You can also explicitly highlight that this is supposed to be Constexpr lambda by putting a Constexpr keyword there if you want. Or you can put it other way around. You will have kind of a different semantic here, but the result will be kind of similar. But it works the same way. The compiler will see that it's Constexpr variable, it's Constexpr lambda, or lambda which could be Constexpr, and it will perform and give us an answer. Good. The next example is C++ 17, is that you have this if Constexpr. And this is a special condition which is enable a lot of metaprogramming, template metaprogramming in general. So basically, let's imagine that we have a function sum which does a lot of accept integers, variadic arguments of it. And then you basically can check, okay, and you can do recursion and you can check how many arguments is there. If it's 0, you basically, okay, you can stop, the else branch would be omitted and you can do whatever you want. So it's basically enabling to decide what to do at compile time, which is quite niche. But generally, as a Constexpr, it works the same. Compiler look at the variable, at the function declaration, and give you a result. Go to C++ 20. There is a lot of cool things here. You get this couple of new keywords, consteval and constinit. Consteval is the way to specify that this function is only available at compile time. You cannot use it at runtime. Constinit is the It's for the variables, so we basically can define that the variable is supposed to be initialized at compile time, but you can change the values of it at runtime. You're now allowed to use new and delete. You're allowed to do try and catch. You cannot throw, but you can do try and catch. And you're allowed to use virtual functions, basically inheritance become available. And you can change the active member of a union. That particular feature is required because now in standard library, we now have a lot of things like a std variant, which is a union, right? Now you're able to use it at compile time. You can use optional, string, vector, and a lot of other things. So let's look at the example. We wrote a sort function which accepts some values. We store them in a vector, we sort it, and we return a vector. Isn't that cool? Now at compile time, we use vector and we can return vector, right? How many people think that will compile? Again, raise your hand. So far, 1. Good. How many people think it will not compile? Okay, 10-ish. And it's the right answer. It will not compile. You will get an error. The result is not constant expression because it refers to result of operator new. Very good explanation. We don't really understand what happened, to be honest. But when you understand it and decrypt that message, you will understand. So you can use vector inside the Constexpr, but all the allocated memory during the compile time should be deallocated by the end of compilation. So you can use it, but you can never return, kind of. You cannot save it into the variable. So unfortunately, we're trying to save it at result, and it's impossible in that way. But we could do workaround. I'm just showing how it could be done. We can make an immediate invocable lambda. We can specifically mark it as that it's const-eval, so only available at compile time. Now we can call our Constexpr function there. We can save the result. And we can now work with that variable. And the compiler will see that, compute, and result will be 1, which is pretty good. The next is C++23. It allows to do a lot of interesting things. It's permitted to say static Constexpr variable. You get the if const eval and some other cool things for metaprogramming. You can even use this to be unique pointer at compile time. So cool. So let's look at this example which we had before, where I tried to save the vector into the result, into a variable. It was not possible to do in C++20, but it's possible to do in C++23. And get ready, there will be a lot of code right now. So this is what you need to do if you want to get a vector from compile time to runtime. And no worries, we will try to go through all the steps here. So the first thing you do is we have a sort function and we have our vector. And now we wrapped it into the lambda and passing as a template variable. Lambda is a variable. We can accept it in our sort function as a variable. And then we can do a couple of things. We have another immediately invocable lambda, which result of that is a static Constexpr. And inside the lambda, we do a couple of things. First, we invoke our lambda to get the size of that vector. Then we call to get that vector. And then we allocated std array with the size of that vector. Then we can copy to that vector. We can perform sort. And then we can return it. And now we static Constexpr auto s is our std array with static storage duration, which means it's okay. Now it's allowed by the language. And then we can return span. So, and that's the way compiler understand, and it will give you a span, and then you can work with that. And during the compilation, it will understand what you want and give you the 1, which is pretty cool. This is not an easy technique. It takes time to understand it, so don't worry if you didn't understand. I really recommend that talk from the Jason Turnon last year. he basically explained this Constexpr's two-step model. It's the whole talk explaining how it works, which is pretty good. I will take time to give you a picture, to take a picture. Yeah. Okay. Constexpr C++26. Now, since the standard is almost ready, we can talk about it. So there are different things which was allowed. You can do casting from void. I don't know why it was not allowed before, but there is some weird limitation which was not allowed, but now it's more and more allowed. You can do structural bindings. You can do Constexpr full exceptions. You can now throw. And if you used a lot of static assert, it has a second argument as a message. Now you actually can format your message. And more things getting standard library Constexpr. For example, atomic variables now available at compile time. Well, that's kind of cool, right? I don't know how it works, but it works. And the last point, all the containers and adapters are Constexpr right now. So, and for that, let's take a look at this. It's so sad that Hannah couldn't attend, because I would love to talk to her about that. I think she did a tremendous job by doing the proposal and actually going to libc++ and implement it. And I will try to press on the link and see if I can actually show you how it looks like. I'm not sure if it will work. 1 second. Yes. And the reason I want to show you, I might try to zoom if it's possible. Yeah, I think everyone can see, right? So this is the branch when Hannah added the Constexpr support for all the containers and adapters. Vector was already map, unordered map, set, queue, wherever you name it's there. And if you go through basically the whole branch, you will notice it's just adding the Constexpr keyword. It requires zero changes, almost. Hmm?
That's also good because Clang accepts anywhere. It doesn't actually do anything with Constexpr.
Yeah. In this particular case, nothing has actually happened. But by just adding the keyword, you bring that everyone else can use it. And that's basically the whole branch like that, which is pretty cool, in my opinion. And you can also see from there is like if you have a code, you can just probably drop a Constexpr keyword, and now you can use it at compile time, with few limitations, of course. Yeah, and also interesting aspect of since I can open that link as well. This is a proposal. There is implementation experience, so she had a personal fork. When she was doing that, she of course was testing it. And when marking set map unordered and unordered map, she ran into UB. So it was quite cool. Just by adding the static Constexpr keyword and adding the tests, she was able to find UB, which is quite cool. So that's kind of a highlight that we can use the Constexpr as a tool to detect UB. Let me go back. Yes, let's go a little bit more into C++26. 1 second, I will put my mouse back. So yeah, I said static assert, you can format your message. You can say std format and you will get it. And if no one's seen what I was showing next, but you've probably seen, so not anymore. But that will not compile, that's what I want to say, kind of how it was. And you will get such a cannot call not Constexpr function std string format. So I don't know why, but they forgot to put Constexpr word there. And there was even a proposal which was supposed to be addressed in C++26, but maybe someone knows here in the room. I don't know why. It's now a hidden story, but they didn't add it. So they have a feature for static assert, but you cannot use it, kind of. That's a bit sad. But hopefully C++29, right?
Would the FMT version work?
Yes, we will come to that. But just imagine we have this proposal. What you will get is that static assert failure, and you get the formatted message, which is quite cool. It's enabled a lot of things for metaprogramming. to give you the real error which explains something. The another cool feature, again done by Hannah, is actually supporting throwing. And just imagine we use stdx, which is like extension, which can actually format things. But what happens here is that when we pass some invalid input, we will get formatted compile time error. I'm not sure how that exactly was put in the wording in the standard, but it's like compilers have to print you an error, printable, understandable what happened. So it's kind of a mechanism to debug Constexpr in a way. But also it's kind of cool, right? You actually finally get compile time errors, which actually tells you what went wrong. Okay, that's basically a quick overview of Constexpr. And now it's time to sprinkle some Constexpr. And if you don't know, it's a Jason Turner always says that you need to sprinkle Constexpr. So let's go to our problems which we've seen and see if the Constexpr will help us. Right? So we just add the Constexpr keyword. We didn't do anything, right? It should work. This is our tests, and we just need to add the Constexpr here as well. And in catch 2 requires runtime, but you have this static require, which will, it's like a fancy static assert, but it will do the job. So now when we run our tests, they fail. They fail, it's amazing. We detect UB, right? But unfortunately, it will just give you error that the std format is not formatable, right? So again, please accept it if someone here from standard committee. But yeah, but let's just imagine that we have our imaginal function which can do that. Then we're actually detecting error at compile time, and and then what you will see is that when we pass the valid input, it will pass, it will not detect anything. It only will fail when there is invalid input has been passed. And it's so the way it works is the same as a sanitizer basically. If you went to that unhappy path, then Constexpr evaluation will detect undefined behavior and it will tell you. And the errors again from Clang, GCC and MSVC sometimes give you really long messages. But it's pretty kind of decent, right? It tells you, okay, well, you're passing the steady string view, and then it says pointer subject to temporary, and basically explain you what went wrong. So compiler actually able to tell you what's going wrong, which is pretty cool. Okay, let's go further. Let's check the reference without a check. So we had this function, we return error code now. And we had this function where we didn't check the version. And let's just say we have this test where the second element is some garbage. So what you get is, again, the version 1, where it's valid input, it will pass. Valid input second will pass. Only when you supply invalid version, then you will fail, basically. And again, you will get a beautiful explanation. You're trying to access value instead of error, which has been initialized. It's pretty decent, right? And for example, we had the out of bound read, right? So if we do another test where we supply only an array of one element, and you run it again, invalid version will. Sorry. Now we can detect it. So yeah, it's okay. Invalid input will basically give us this, that it will tell you you're trying to access to element 1, meanwhile it's out of bound. So the compiler tells you everything, which is like, that's what we wanted, right? Let's go further. Memory leak. Remember there was malloc and free, right? So we just sprinkle Constexpr, and they run the tests. And they're failing, but they're failing that file read is not Constexpr. And this is one of the things which we now start to notice with Constexpr. It will tell you, okay, malloc is not Constexpr, free is not Constexpr. So this is our first time we cannot just sprinkle Constexpr. We need to actually Constexpr everything, kind of. So in this particular example, let's just imagine that we have some iFile interface, which is Constexpr compatible. It has a virtual function which marks as Constexpr. And then we go and replace malloc with new and delete, because new and delete, and then we basically can, yes?
You have the wrong delete.
Perfect, someone says that I have a wrong delete, that's perfect, but let's see if Constexpr will catch it, right? So I'm running valid input, passing again, and the new condition we check, we will get, okay, the constant expression because of, like it basically tell you, you didn't deallocate it. And for the delete, it will tell you that you're using a wrong delete, which is pretty good, right? So let's just summarize what we've seen right now about Constexpr and our case studies. So we detected all the issues at compile time. They generally work as sanitizers, but at compile time. And you need to have a good test coverage. Without that, it doesn't really help you at all. And you need to change, split, modify the code to be Constexpr compatible. And that applies to a lot of actually things, because there are some limitations in a language, in a standard library, and for example, Constexpr things should be in headers. So you don't really maybe want everything to be in headers, right? It slows your build time. So, but it works. Let's talk a little bit about limitations. So there is language features which are not supported by any C++ standard. Like no IA, you cannot open a file at compile time, you cannot do a network request at compile time. I put a star on the file system because technically we have hashtag embed right now, which cannot give you the file content, but that's not a C++, it's a preprocessor, right? In that regard. You cannot do any threading and no support for coroutines, unfortunately. So in this particular cases, if you're using the threads or coroutines, you have to like split the functions and do these things. Library features. I try to actually understand what kind of library features are missing, and I come up with this answer. I don't think anyone knows, because technically if you forgot to put the Constexpr in any functions and you go to that path, now you cannot use it. So I don't think it's super easy to go through the standard library and find where you forgot it, right? Yeah. If someone knows, please tell me. I will put it in a slide and credit it to you. On ecosystem. So I think generally tooling is missing any kind of support of Constexpr, and like you cannot profile Constexpr easily, you cannot debug it, you cannot basically do anything. Except somehow C-Line recently introduced the Constexpr debugger. I have not tried it, but I went through the documentation. Looks like it does it somehow. I don't know how. But it's quite cool. So tooling is getting, but I would still, it's only C-Line. If you use anything else, it doesn't work for you. I would say missing Constexpr in third-party libraries. So like range v3, for example. If you're not using standard ranges, and range v3 is very lack of support of Constexpr. It's like some words are somewhere Constexpr is not there, and that just doesn't work. And I would say test framework integrations, and this is what I'm going to talk now to show you how hard it is actually to write the tests. But we will try to learn how to do that. So yeah, how to test Constexpr code. Is everyone familiar with Sketch 2 by now, right? You have a test case with the name, and you have this one macro require. And when you basically, again, we're using the best build system ever, CMake. So we configure the project, we build a project, we run the project or the tests, and we get such type of error. This is your test, this is the line which failed, and you will get actually the message, what's failed there, right? So when it comes to the Constexpr stuff, we're using static require. And static require, as I said, it's a fancy static assert. So there is a little bit difference what we'll see. And I try to put a fancy animation. How many of you using IDE? Can you put the 5 people? No, more? Okay, almost everyone, I guess. How many of you using editor plus ADE plugins, like give you code completion and everything? Yeah, rest of the group, good. So we're all using some kind of integrated IDE, either you made it by yourself plus like editor plus plugins or something. Yes. So the reason I'm saying is like, if you open this particular file in your editor, the first thing you will see is like this, something wrong, right? I think most of the IDEs highlight with the red curvy line. And if you put your mouse cursor on that, you will get this pop-up window. It says static assert, it failed. So the reason I want to show it is that we didn't even compile the code. We didn't run it. We didn't do anything. The IDE or your editor did it for you already. So that's a kind of cool thing. You can just write the code and immediately see if it's working. You don't even need to wait of building. IDE does it for you, which is, I think, a pretty cool thing in general. And by the way, I've been using this technique for testing the code for a long time right now. I really can say it speeds up your progress because you don't anymore wait for the build. You don't need to switch the windows or press any buttons. It's just coding and it just tells you. But it has a caveat, so we will go into the details right now. So usually we are not particularly testing like such examples, right? We usually have some classes, we perform some actions. In this case, we have array, we're trying to sort it, and then we do try to check if our algorithm or function works as expected, right? And in case of catch, you will get such a nice explanation. That's the line that failed, and it will tell you the 3, not what you expected, right? So let's try to do the same trick with static require. And surprisingly, it will not even compile. And the reason it will not compile because static require is a static assert in the end. And the static assert can work only with Constexpr variables. In our case, the data is not defined as a Constexpr. So, and you will get this error trying to explain you that you need to declare it with Constexpr. Okay, let's just do what the compiler says, right? We will add the Constexpr and try to compile, and now we will get an error that, oh, you cannot call sort because your Constexpr variable is const, right? So you cannot actually perform any actions. Okay, what we can do to work around that, again, go to that trick. We can create immediately invocable lambda and put our test there. Now our variables technically in compile time, right? We should be able to use them. And yeah, we marked it as const eval and we invoke it immediately, right? So, but unfortunately, if we try to build it, it will also not work. So it will not work because even if your variable is defined in Constexpr context, it's still not a Constexpr variable. So you cannot use it in static assert. So the way to work around it is like we can return our data stored in Constexpr variable, and then we can do it, perform our static require test. And we will get such error. And if you look at the result, 0 = 4, right? We don't actually get what's get wrong, right? We don't, when we did runtime, we actually saw that it was 3 = 4, but now we actually don't see. And luckily, compiler is able to deduce it for you. They can actually print it, which is pretty cool. Unfortunately, it only works for simple types. If you have your custom structure, something more than just built-in types, it's like a std string, it will not print it anything to you. And you basically, what you need to do is run back, remove the static from the require, and then run it, build it and run it to see the error, which is pretty sad. So, but ideally, we would love to see something like that at compile time, right? The question is, yes?
Do I need the Constexpr keyword here in this example?
Yes, you need. Because otherwise, it will be like you invoking a lambda, and it will return your runtime variable then. So in this case, you have to tell, no, it's a Constexpr result. So you have to keep it. Yeah. So let's just forget about static require, just write it our own. We could do something like that, right? We can actually, now with C++26, we can format. But we all remember that std format doesn't work, right? And this is where it comes, FMT format. For those who doesn't know, std format is based on FMT format library. And FMT format library allows you to format messages at compile time. So that feature was introduced quite recently from the last version 12. You can do FMT format, which returns you a std string. And you can use FMT static format if you want to, like the same two-step model of Constexpr step model to get the string view. I think it will give you as result. So it's pretty cool. And then you will get your error like this. And for those who are just curious, if you don't have for some reason format library version 12, it was still possible to do it. I think it was 11 and even maybe version 10, I'm not sure, but 11 for sure. And it's just you need to use format 2, store it in a string, and return. So it will just work. You don't need to do anything. And the reason why FMT 11 didn't support FMT format because there was just missing Constexpr keywords. If you look at the PR which introduced that feature for FMT format, it was basically just adding Constexpr keywords, nothing else. Okay, so we get our beautiful result, which is quite good. But let's go to reality. In reality, you don't really do, I think most people don't do one require statement. They do several operations, they do several require statements. I think, yes?
That's very bad testing practice.
I would agree with you, yes. I wouldn't encourage to do that, but I said real life, right? In real life, we do this. It happens. So if it's possible to do one statement, do it. If it's not possible, let's see what we can do with that. So a lot of code, but look at that. What we could do, again, we're still using the lambda. We just return expected or string as an error. And we can say static assert result has value or error. Should work in theory, but we remember, right? Std string allocates. It should deallocate when we go out of the Constexpr. So we can apply this two-step Constexpr model again, where we actually supply our test case as a template argument. And what we'll do, it's basically run your test case once, check if there is a success or actually there is an error. If there is an error, it will take the size of that, allocates a std array for you, and like run it second time to copy the error there and return to you. And then we will get a beautiful error. Yeah. Yeah. But there is one question. What if you don't have C++26? I'm not sure. How many of you are using C++26 right now? 0 people. C++23. 2, 3, 4, 5. Cool. C++20. Okay, majority. So I think assume everyone else below it, right? So we see that majority doesn't use C++26, so 23. So what to do for those who use C++20 and 17? A bit trickier, but possible to achieve. But I will show you C++20 solution, just for you know. So we can supply our helper, which takes the same arguments. And it's a concept. I will show how it looks like. It looks like this. We have two concepts, one called static verify, which accepts Boolean and static string. And if you don't know, static string is basically usually a smart wrapper around std array to pretend to be a string kind of. I think in standard we'll have either in place string or something like that. But it's pretty common to see it. That string doesn't allocate anything. So yeah, and then we call another concept. And the way it works is that, I will show you a quick example, is that let's just imagine that we have a string and we call our static assert static verify. And then you get an error, and it will tell you first, it will tell you what's happening and try to evaluate the concepts. And because the concepts, I think it was in a standard, but correct me if I'm wrong, but it says that compiler should provide more verbose output. And that's why the second string you will see, it says the second concept, and it will print you actually as the string. It is workaround, but available, of course. And I think if you work in C++, you kind of get used to workarounds. Except if you're not using MSVC compiler. MSVC compiler, for some reason, decided to print you the character number, or integers. I don't know why. I tried so many different options to trick it, but it didn't work. So yeah. So if you're on MSVC, well, I mean, you can ask ChatGPT to give you a string out of it, or write a small script, you know. But in general, it's cool. And that solution works with C++ 23, 20 as well, and you can do 17 as well. But you need to, instead of using concept, you need to have a function which is deleted. And then the compiler will say, you're calling a deleting function and also print you that string. So there is workaround. You can go lower on GCC 10, I think, and Clang 17 or 16 to make it work. Yes. But now let's quickly take a look what we have. I mean, who wants to write such kind of test? You kind of did a lot of manual work. This is not anymore a test, right? Ideally, we should have something like that. And the framework, test framework should say, okay, this is a static test, and yeah, everything else should magically work. And technically, it's possible. It just requires some work and PRs and patches. I'm out of time. Good. Quickly, summary. Constexpr is memory safe as subset of C++. It partially replaced sanitizers and doesn't a lack of concurrency support. It partially replaced static analyzer that doesn't work without the tests. It requires adaptations. You need to sprinkle Constexpr and refactor your code. And it's built-in feature which works out of the box. That's it. And one more slide. If you want to learn, look at these libraries. And Jason Turner and Ben Dean, they post a lot of cool things about Constexpr. Thank you, and questions. Yeah, there is a question.
Maybe one.
Yeah.
So, as someone who has written a lot of static asserts and Constexpr tests, what I observed sometimes is when you make a change and now many test cases fail and they all produce compile errors, and that is when things get a little bit messy because figuring out why it's bad beyond the first one is really tricky.
Yeah, so the question or comment is that it's when you write a lot of Constexpr tests, static tests, it's very hard to figure it out when something fails, and it's true. We don't have a lot of tooling, but that's why I'm showing this kind of, if you trust your IDE and you're actually able to provide a nice message, and you use this providing the errors, you can actually see it. But you need to adapt your code to use like std expected all the time and return if something goes wrong. But it's true, it's very tricky and it's very hard. And sometimes I remove the static required to be required and use GDB if it's needed, right? But I haven't tested CLine how it works. Maybe it's actually solved the problem right now. Yes. Any more questions? Yes. Yes.
For the sanitizers, we can also use fuzzing. Do you know if anyone has thought about fuzzing?
Yeah. Yeah. So the question is that with sanitizers we can use fuzzing. How to do with Constexpr the same. So the answer is you need to prepare a huge data set, which would be in C++, and then you have your test, and then you supply that. Like basically fuzzing is like you're calling the function, right, and supply different things. In this case, you need to have a compiler, have your test, and another file which has all these pre-generated values, input values. It is possible, but not cool, I agree.
There are some Constexpr random library.
Oh, right. I didn't know about that. There was a suggestion there is a Constexpr random library. Yeah. Cool. There is one more question, but maybe it's we're out of time. I don't know.
Yeah, I'm out of time.
Yeah, then just come to me and we'll talk. We'll be here. I will be here all the time. Yeah. Thank you.